Have you ever looked at something really small through a magnifying glass? When you bring the magnifying glass near the object you're looking at, it appears much, much larger. This video explores simple lenses and how they create images, such as the one you see when you look through a magnifying glass. After completing this assignment, you should be able to identify qualitatively the relative locations of an object and its image formed by a single lens, and determine whether the image is real or virtual, and upright or inverted. Getting the most out of this video requires a solid understanding of refraction, Snell's law, which relates the direction a light ray travels to the index of refraction of the material as it passes from one medium to another, and image formation by mirrors, including the definitions of object distance, image distance, focal point, and principal axis. A solid understanding of lenses is important because they are used in many optical devices that you might encounter every day, such as a telescope, eyeglasses, and the camera in your smartphone. Consider the light rays that leave a burning candle and spread in all directions. If this candle is next to a window, the rays will still spread in all directions, but the ones that pass through the glass will be refracted. Consider one of these light rays, which travels from the candle to the window at an angle of about 15 degrees above the horizontal. In which direction will it bend after it passes from the air into the glass? Will it bend down so much that it actually travels downward? Will it bend down and still travel upward, but at less than 15 degrees to the horizontal? Will it not bend at all? Or will it bend upward and travel at an angle of more than 15 degrees to the horizontal? The light will bend down slightly and still travel upward, but at less than 15 degrees relative to the horizontal. The light rays will bend, but all of the refracted rays will still be spreading apart. If you were looking through the glass from the other side, you would see the candle, but not at its actual position. Instead, you would see it from where the rays appear to have come, which is farther away than the actual object. This type of image is called a virtual image, since the rays do not actually come from this point. They just look like they do. If the glass is not flat, though, the rays can bend downward relative to the horizontal. Consider two light rays from a candle to the left of a single lens. The lower ray passes through the lens at the center of curvature where the principal axis crosses. If the lens is thin enough, the small bend the light makes going into the glass is just the opposite of the bend it makes coming out of the glass. So the ray is almost a straight line. However, the top ray travels parallel to the principal axis and bends downward when it passes through the lens, since it hits the surface of the lens at a spot that is more curved. If we didn't know the lens was there, both of these refracted rays would appear to come from a bigger candle located farther to the left of the lens than the actual candle. This is how a magnifying glass works. If we move the candle back more and more to the left, the top ray still travels parallel to the principal axis, but the bottom ray travels at a smaller angle relative to the principal axis in order to pass through the lens at the center of curvature. As the candle moves left and the two rays become more parallel to each other, the point at which the refracted rays appear to meet will be farther back from the lens, and the virtual image will be larger and farther away. Eventually, the candle will be at just the right spot that the light rays passing through the lens after refraction will be parallel to each other and never intersect. The image will be at an infinite distance behind the lens. This occurs when the candle is at the focal point of the lens. The distance between the focal point and the lens is f, the focal length of the lens. If we move the candle back farther to the left of the focal point, the bottom light ray will refract so that it intersects the top one on the right side of the lens. A person looking at the candle through this lens would see the real image rather than the actual object. The real image would also appear upside down, inverted, compared to the actual object. If we continue to move the object farther away from the lens, would the real image become larger? Would it become smaller? Or would it stay the same size? The correct answer is that the real image gets smaller and closer to the lens as the candle moves farther behind the lens. Eventually, if we move the candle far enough behind the lens, the light rays that reach the lens will be almost parallel to each other and will refract to intersect at a single spot. That spot is the second focal point of the lens, and it's located the same distance on the right side of the lens as the first focal point is located on the left side of the lens. All parallel rays of light striking the lens converge at the focal point. The distance p from the lens to the object and the distance q from the lens to the image are related to the focal length f of the lens. The sum of 1 over p and 1 over q is equal to 1 over f. For example, say a lens has a focal length of 12 centimeters. When an object is placed 30 centimeters away from it, a real inverted image will be formed at 20 centimeters on the other side of the lens. If the object is closer than the focal length, say 6 centimeters, the equation will give a negative answer for the image distance, in this case, minus 12 centimeters. This is what happens when there is a virtual image. Let's review what we've learned. We set out to identify qualitatively the relative locations of an object and its image formed by a single lens, and determine whether the image is real or virtual, and upright or inverted. Using the relationship between the object distance, p, the image distance, q, and the focal length, f, we can design instruments that not only magnify small objects, but also bring very distant objects into closer view.